This video is on tangent line approximations. We will review how to write the equation of a tangent line and then use the equation of a tangent line and something called a differential to approximate or estimate a function. Notice that there is this new word here, differential, and I'll explain what that is also. Let's take the example, f of x equals sine of x plus 1. And I'm going to take a few x values. We're going to take x equals negative 0.5, negative 0.1, negative 0.01, 0, 0.01, 0.1, and 0.5. And now, what if I told you that you could plug in all of these numbers into this function and estimate the actual value of that function to within like 4 decimal places without a calculator? Yeah, that sounds pretty exciting, doesn't it? Some of you are probably like, no, whatever. But it's kind of cool to be able to do this without a calculator. Like, do the sine of negative 0.5 plus 1 without a calculator. Hey, that's kind of exciting. Here's how we do it. What we do is we take the tangent line equation. So, let's figure out where we should write our tangent line equation. Well, I'm going to tell you, we're going to write it at x equals 0. And the reason we are going to write it at x equals 0 is because we actually know what f of 0 is. What is f of 0? Well, it's sine of 0 plus 1. The sine of 0 is 0, and so f of 0 equals 1. Alright, let's write our tangent line equation. We'll have y minus the y value, which we just decided was 1, equals the slope. Alright, we'll leave it blank for now. And then x minus the x value is 0. Let's fill in the slope. So I say slope, you think, ha, derivative, yay. So we find f prime of x. F prime of x equals cosine of x, because the derivative of sine is cosine, and the derivative of a constant that is added or subtracted is 0. So we get cosine of x. But I don't put in cosine of x because that's not a number. Remember that your slope must be a number. So I need to plug in the x value into cosine. So f prime of 0 is the cosine of 0, which is equal to 1. So my slope is actually 1, so 1 goes in there. This gives us the tangent line. I'm going to solve for y. It gives me the tangent line equation, y equals 1 plus 1 times x minus 0, which is just 1 plus x. So now I'm going to fill out my chart. I'm going to make it all charty now. And now all I have to do is just plug in these numbers into this very easy tangent line equation. Check it out. 1 minus 0.5 is 0.5. 1 minus 0.1 is 0.9. 1 minus 0.01 is 0.09. No, it's not. It's 0.99. What am I talking about, Mr. DRAM? 1 plus 0 is 0. 1 plus 0.01 is 1.01. 1 plus 0.1 is 1.1. And 1 plus 0.5 is 1.5. That was really easy. So what does this mean? Well, it means that the values of f of x, so the values of sine of x plus 1 are very, very close to these numbers that we got. Well, how close? Like, are we within, like, 1? Or 0.1 or 0.001 or 0.0000001? Well, let's find out. And the way we're going to find out is we're going to take our calculator and actually figure out f of x equals sine of x plus 1. Now we're just plugging in the x values into the actual function to see what we get. And the numbers that we get are this: 0.521, 0.9002, 0.99, those are 9s, 0.0002. This one we get 1. Hey, I did this wrong. Ah, gosh. 0 plus 1, Mr. DRAM, is actually 1, not 0. Duh. Over here we have 1.0099998. Here we have 1.0998. And here we have 1.479. I just did all those on my calculator and wrote them out. So check it out. at the point of tangency at x equals 0, the y values are exactly the same. And we kind of expect that to be true because it's the point of tangency, so they should be the same. And if we go a little bit off of the point of tangency at x equals 0, if we do a very small change in x, notice that the y values are pretty darn close to each other. Like the actual y value is 1.0099999998, and our estimation was 1.01. That difference is very small. It's like 0.000002. And there might be some more zeros. No, that seems like enough zeros. Yeah, that's the difference in the y value. And that's really, really, really small, and most of the time you're not dealing with that level of precision. So our tangent line equation, which was very, very easy to do because all you have to do is just do sine of 0 and cosine of 0, gives us a pretty good estimation for sine of x plus 1. Notice, however, that if you go farther away from 0 to like 0.5, notice that our estimation becomes less good. Okay, this difference here between these two values is no longer like 18 digits of accuracy. It's more like, 0.02, so we're a little bit closer. And if we go really far away, let's say we choose like x equals 50 just because we could. And if I plug that into my equation for y, remember y was 1 plus x, I'd get 51, okay? But the sine of 50 plus 1 is 0.7376. And so notice that our tangent line approximation is only good when we are close to the point of tangency. In this case, that point was x equals 0. If we get too far away from 0, guess what? Our approximation isn't going to work anymore. Here's a graph of what we actually did. Here's sine of x. Okay, it's all loopy and stuff. And this is, remember, that's sine of x plus 1, so it's been shifted up 1 unit. And then our tangent line, we had our point of tangency at the point 0, comma 1, and then the slope was 1. So the tangent line looks sort of like this, like that, and then going down like that. And check it out. If we pick x values that are close to 0, notice how close the blue original function and the red tangent line are, right? They're pretty darn close. That's why when the values were close, we got why the difference was very small. When we got farther away out here, notice that that difference increased substantially, right? As we get farther and farther away, the actual difference between the values gets bigger and bigger, just like we saw here. The difference here was 0.000002, and then as we get farther away, the difference increased a lot. And if we went really far away, this difference is like 50.2. Like, that's a huge difference. The point of this is that the tangent line is easy to find, and we can use the tangent line, which is easy to find, to approximate complicated functions. This function, not so complicated. It is complicated without a calculator, which makes the tangent line easy because, 1 plus x, like you could do that in your sleep, and that's easy. But sine of x plus 1 in your head isn't easy. So it's a matter of making things easier to approximate, but remember that this only works if x is close to 0. Here's another way to use the tangent line of a function to approximate the original function. So let's say we have some function, looks like this, and I have an original point here, and this is at x comma f of x. And I'm going to say we're going to go out a little bit this way, and this length is going to be delta x, which means that this value here, this blue distance, is the difference in y values, because I'm taking the original y value and then this upper y value, and this is going to be delta y. So delta y is the actual change in, sorry for the scribbles, it's the actual change in y. Now I'm going to draw my tangent line. When I draw my tangent line, notice that when we're close here, that the tangent line is pretty close to the original function, like we want it to. And this is sort of a bigger picture just so we can see what's going on. But notice that I get this little red triangle here. So what I'm going to do is I'm going to examine this red triangle. Here's the red triangle. And notice that I can find slope by doing rise over run. Well, because it's the tangent line, I know that the slope of this tangent line is f prime of x, because you know the slope is derivative. Well, f prime of x, another way to write f prime of x is dy dx. So I can split up the dy dx. And so the rise of this function could be dy, and the run is going to be the dx. So see how it's rise over run? I can label the parts of this triangle. When I put those estimations back on our original picture, notice that the dx and the delta x match up exactly. And so we get this relationship that delta x equals dx for the thing that we're going to do. However, dy, which is this distance here from this point down here to this point up here, dy does not equal delta y. However, notice how they're kind of close. And if we get closer and closer and closer as delta x shrinks, they're going to be approximately equal. So the relationship that we're going for is that delta y is approximately equal to dy. Okay? Recall that delta y is the actual change. Dy is going to be the estimated change. This begs the question, how do I find dy and how do I get it by itself? Good question. Here's what we're going to do. We're going to say, well, dy dx is equal to f prime of x. And watch very closely, using algebra here, move the dx over. So dy equals f prime of x times dx. This is an equation, and this dy and this dx separately are called differentials. Kind of sneaky. All right, let's see how to use differentials in a problem. Let's say you want to impress all of your friends, and you want to tell them that you know how to find the square root of 16.5 and approximate it to within 4 or let's say 3 decimal places. Okay, seems like a pretty cool trick, huh? Well, you don't know how to do it yet, but I'm going to show you how to do it. You're going to use differentials. Do we know the square root of a number that's close to 16.5? The answer is yes, we do. We know that the square root of 16 is 4, and we're going to use that fact to help us. So to use differentials, we're probably going to use this equation at some point, so we need a function. What should be our function? Well, how about f of x equals the square root of x? And what x value do we care about? We don't care about 16.5. The x value that we're going to pick is the x value that we know the value for. It's going to be 16. So let's do this. dy equals f prime of x times dx. All right, well, let's just fill in the blanks. So f prime of x is the square root, or is the derivative of the square root of x. So when I find f prime, let's see, f prime of x is going to be 1/2 x to the negative 1/2. There's no chain rules because it's just x. So I'm going to get 1 divided by, and then remember a negative exponent goes in the bottom, and a 1/2 is the square root. So I have 1/2 times 1 over the square root of x times, dx. Oh, remember that dx was equal to delta x from our pretty picture back here. Ta-da! Delta x equals dx. Well, the delta x is going to be the change in the x value that we want compared to the x value that we have. That change is 16.5 minus 16, otherwise known as, so delta x equals this, otherwise known as 0.5. And I'm going to write that as 1/2. It'll make my math easier. And basically we're almost done. I just need to know what x is. Oh, there it is. X is 16, so I plug it in. And so I get 1/2 times 1 over the square root of 16 times 1/2. And when I multiply this all out, square root of 16 is 4, so I get 1/2 times a 4th, which is 1/8, times 1/2, which is 1/16. So dy is 1/16. What does that mean? It means that I'm starting at the point 16, 4. Okay, and I'm approximating the new y value. Okay, the new y value, we said that dy was 1/16. Well, keep in mind that, remember, dy was approximately equal to delta y. So the new y value is going to be the old y value, which was 4, plus the change in y, okay, which is going to be approximately equal to 4 plus dy. I'm just substituting dy in for delta y, and dy was 1/16. So we have 4 plus 1/16. If you know your fractions, you know that this is 4.0625. Okay? The significance of this is that we just estimated the square root of 16.5 is approximately equal to this number, 4.0625. And you just estimated that to like 4 decimal places. Let's see how accurate we were. If I take my calculator and I calculate the square root of 16.5, the actual square root is approximately, because it's infinitely long, but I got this. And our estimation was the 4.0625. And so you can see that we're pretty good. We're close. We're accurate to 1, 2, 3 decimal places, which is pretty good for doing some pretty simple calculus. As a very side note, you might see this in the future, but the dy, this differential, is synonymous with something called propagated error. And we'll look at some problems in class that have to do with propagated error, or if you see it before, now you know how to find it.